In this presentation, I will discuss electrical power. Electric power is a measure of the rate at which an electrical device does work or expends energy. For example, a powerful elevator will get you to the 20th floor of a building quickly, and a powerful portable heater will bring a room to the desired temperature quickly. Power is found by dividing the work output, or energy expended, by the elapsed time. Power is measured in joules per second, or watts. Now I'm going to transfer the power equation so that it includes voltage and current. Since electrical work, that is the product of voltage and charge, we can replace the W with V times Q in the equation. Since Q over T is current, we see that the power equation can be found by multiplying voltage and current. And since Ohm's law tells us that V equals IR, replacing the V with IR in the equation, we get a new form of the power equation, P equals I squared times R. The last equation that can be used to find power is P equals V squared over R, where V is voltage and R is resistance. The variables given in our problem will determine which equation of the three we can use to get our solution. Let's try a problem and see if we can pick the right equation. A series circuit contains two lamps and a battery with a potential difference of 1.5 volts. If the current in the circuit is 0.10 amps, at what rate does the circuit use energy? Now the question asks us to find the rate at which energy is used. Since that is the definition of power, we're going to need to find an equation with the two variables mentioned in this problem, voltage and current. The equation that will help us find power is the first one, P equals VI. Plugging in the data given, we get the answer 0.15 watts, or if you forget the unit for power, you can write 0.15 volt amps. Let's now use the equations we have been given to find the relationship between power and resistance. If we look at the first equation, we would conclude that power and resistance have a direct relationship, but then we look at the second equation, we would conclude that the relationship is inverse. Actually, power and resistance sometimes have a direct relationship, and under other different conditions, the relationship is inverse. So what does this mean? If the two components in a circuit have the same current, then the relationship is direct, and the component with the greater resistance would use more power. If the components you are comparing have the same voltage, then the relationship would be inverse, and the component with the smaller resistance would have or use the most power. Once again, if the components you're looking at have the same current, like a series circuit, the more resistance, the more the components consume power. If the components have the same voltage, like a parallel circuit, which the device with the smaller resistance would use energy at a greater rate. Let's see if you can apply what you just learned. In which kind of circuit would a 5 ohm resistor be brighter, more powerful, than a 10 ohm resistor? Well, in the example, the brighter light bulb had the smaller resistance. That's an inverse relationship. Now, once again, if the 5 ohm resistor is brighter, then there must be an inverse relationship, and the voltage of each component must be the same. This means that the two components could very likely be connected in parallel. In case you forgot, this is what a parallel circuit looks like. Each bulb has a voltage that's equal to the voltage source that provides the energy for the light bulbs. And this is the end of my presentation on electrical power, or the rate at which energy is expended or work is done by an electrical device.